Uranium. It's an element that holds two incredible and frankly terrifying destinies. On one hand, it's a source of immense clean energy, but on the other, it's the core of the most destructive weapon we've ever created. So today, we're going to trace the journey of this powerful material, all the way from deep inside the Earth to its two vastly different fates. Okay, let's just dive right in. It really all comes down to this one question. What you're looking at here is a single uranium fuel pellet. And yeah, it's only about the size of a peanut. So how on earth is it possible that something this tiny contains such a staggering amount of energy? Well, because packed inside that one little pellet is enough thermal energy to produce 1,000,000 kilowatt hours of electricity. To give you some idea of what that means, that's enough to power the average American home for decades. I mean, the scale of it is it's mind-boggling. To put that into perspective, a single pellet holds the same energy as nearly a ton of coal, or 150 gallons of oil. It's this incredible energy density that makes uranium so valuable, and of course, so dangerous. So where does this all even come from? Well, the whole story starts deep, deep underground. Before it can power a city or become a weapon, it has to be pulled from the earth as just raw, unassuming rock. You know, most of the world's uranium actually comes from just a handful of places, with Australia, Kazakhstan, and Canada leading the pack. It's extracted from a mineral called uraninite, and they use everything from massive open-pit mines to deep underground tunnels. And get this, some of those mines are incredibly rich. In Saskatchewan, Canada, for example, there are certain deposits where the ore is 100 times more concentrated than the global average. Okay, so once the ore is on the surface, it's sent to a processing mill. There, it's crushed into sand, mixed with acid to dissolve out the uranium, and then it's purified. The final step is to dry it all out, which leaves you with this bright yellow powder, famously known as yellow cake. But believe it or not, this is just the beginning. The really crucial part, that comes next. This is where the science gets really, really fascinating. See, natural uranium isn't actually very useful on its own. To unlock its potential, it needs to be processed in a very specific way, and that process is called enrichment. So what even is enrichment? Well, natural uranium is made of two main types, or isotopes, U-238, which makes up over 99% of it, and U-235, which is just this tiny fraction, about 0.7%. But here's the kicker. It's that U-235, that tiny fraction, that's the only one that can actually sustain a nuclear chain reaction. So enrichment is simply the process of upping the concentration of that all-important U-235. And this chart right here shows you exactly where those two destinies fork. For a nuclear power plant, you only need to enrich the uranium to about 3 to 5% U-235. But to create a weapon, you have to crank that all the way up. We're talking over 90%. This huge difference is the dividing line between creating energy and creating a bomb. So how in the world do you separate atoms? First, that yellow cake is converted into a gas. This gas is then pumped into thousands of centrifuges, which spin at absolutely insane speeds. Because U-238 atoms are just a little bit heavier, they get pushed to the outside wall, while the lighter U-235 atoms gather near the center, where they can be siphoned off. This is an incredible engineering feat, by the way. You need materials that can withstand spinning faster than the speed of sound without just flying apart. So from here, the enriched uranium is ready to follow one of two very different paths. All right, so let's follow that first path, the low-enriched uranium, the stuff that's destined to become fuel for clean, carbon-free electricity. So over at a fuel manufacturing facility, they take that enriched uranium powder and press it into those little pellets we saw earlier. These pellets are then baked or sintered in a super hot furnace to make them incredibly dense and stable. Then hundreds of these pellets get stacked into these long tubes made of a special metal called zirconium, which are then sealed up tight to create a finished fuel rod. And we're not talking about just a few rods. Thousands of these fuel rods are bundled together and loaded into the core of a nuclear reactor. Inside, a controlled chain reaction begins. Neutrons split U-235 atoms, which releases massive amounts of heat. That heat is used to boil water, creating high-pressure steam that spins giant turbines, and that generates electricity for millions of people. It's a beautifully complex and powerful process. But now, we have to turn to that second path, the darker one, the path that takes highly enriched uranium back to World War II and a top-secret mission known as the Manhattan Project. See, the discovery of nuclear fission back in 1938,
That kicked off an absolutely frantic race. Terrified that Nazi Germany might develop an atomic weapon first, the United States launched the Manhattan Project in 1942. The physicist J. Robert Oppenheimer was put in charge of the secret lab at Los Alamos. But this wasn't just a lab. It was a secret empire, employing hundreds of thousands of people across hidden cities built from scratch, all with one single urgent goal: build the bomb. And the physics here is what makes all the difference. Unlike a power plant, which needs a steady, controlled reaction, a bomb requires the exact opposite. You want an uncontrolled chain reaction that releases all of its energy in a fraction of a second. To do that, you need highly enriched weapons-grade uranium to create what's called a supercritical mass. Basically, you have to pack enough fuel so tightly together that the chain reaction explodes instantly instead of being contained. And the result of all that effort was this device, codenamed Little Boy. The design was surprisingly simple, really. It functioned just like the barrel of a gun. It held about 64 kilograms of highly enriched uranium split into two main parts: a hollow target and a smaller bullet that was designed to be fired right into it.
And here is the terrifying final sequence. After being dropped, sensors would detonate the bomb at a very specific altitude. A conventional explosive would then fire the uranium bullet down the barrel. When that bullet slammed into the target, the two pieces combined to form that supercritical mass, instantly kicking off an uncontrolled nuclear chain reaction and an explosion of unimaginable power.
The successful creation of this weapon changed the world forever. It left humanity with an awesome and, frankly, terrifying new responsibility. Picture this: July 16th, 1945, out in the New Mexico desert. Oppenheimer and his team gather to watch the Trinity test, the first ever detonation of a nuclear weapon. And as he watched that mushroom cloud rise into the sky, the sheer scale of what they had unleashed became terrifyingly clear. In that moment, he famously recalled a line from the Hindu scripture, the Bhagavad Gita: "Now I am become death, the destroyer of worlds." He knew, and the world would soon learn, that nothing would ever be the same again.
And so that leaves us with the question we are still grappling with today. From a single element pulled from the earth, we forged both a source of clean power and a weapon of total destruction. Humanity unlocked the atom. The challenge that remains is whether we can truly control its dual legacy.